It can be said that calculus is the language in which science is written. That's because derivatives give us a powerful way to describe the relationships between variables, both quantitatively and qualitatively. In this lesson, we're going to look at one of the most common ways that those relationships are expressed: differential equations. Making connections is an important part of doing mathematics. If you look at math as nothing but a collection of disjoint facts to be memorized, it gets kind of difficult to keep them all straight. It kind of feels like holding onto a bunch of ping pong balls, trying not to drop any of them. But if you can make connections between those facts and ideas, it's like having glue that holds all the ping pong balls together, making it easier to hold them all. Okay, maybe that's a weird metaphor, but it's the first one I thought of, so just go with it. One type of connection we've certainly talked about a lot in this course is how math relates to real-world applications. But I think it's just as important to see how math relates to other parts of math as well. When you're learning an unfamiliar topic, like, say, rational functions, it helps to see how that relates to something more familiar, like fractions. What you've learned from one thing can give you insight on how to deal with another. Though, of course, the new situation will often have its own quirks as well. Actively seeking to construct those connections is the difference between merely learning mathematics and truly understanding mathematics. Keep that in mind as we discuss our next topic. Important question. Are you ready for the zombie apocalypse? You should be. You never know when it's going to happen, and it's always good to be prepared. In fact, imagine this situation. Imagine Oglethorpe University is now the site of a zombie outbreak. Or if you go to a different school and you're watching this on YouTube, substitute your school here. Here's what we know. On day 0, 10 students were noticed to have been turned into zombies. The next day, that number was up to 13 zombies. So how long do we have before there are 1,000 zombies roaming around campus looking for brains to eat? We could wait a few more days to collect some more data points and try to figure out what model would best fit our situation. But come on, it's a zombie apocalypse. We don't have time for that. Every moment we waste could be life or death for some poor student. Or, I guess, undeath. Anyway, we need to somehow find a way to develop our model from first principles, from some kind of understanding of why the population of zombies might grow the way we think it does. After a little bit of thought, we might decide that it's reasonable to say that the rate at which zombies spread could be proportional to the number of zombies already among the student body. In other words, more zombies means more infections, which means more zombies, which means more infections, which means... Okay, you get the idea. We can actually capture this exact idea by using derivatives. We'll use z to stand for the population of zombies. So then the population growth rate is dz over dt, the derivative with respect to time. So when we're saying that zombie growth rate is proportional to the population, we're saying that dz over dt is equal to some constant of proportionality k times the population z. What we have here is called a differential equation, which is essentially just an equation that involves derivatives in some ways. I think it's useful here to take a step back and compare differential equations to the algebraic equations you're used to. In an algebraic equation, you're given some information about a variable, and your goal is to figure out any values of that variable that make the equation true. Similarly, with a differential equation, you're given some information about the derivative or derivatives of some function, and your goal is to find a function that fits that description. Okay, how might we go about solving this particular differential equation? Well, it turns out solving differential equations isn't easy. It requires some trial and error, as well as some experience recognizing certain patterns. We'll learn a technique for solving differential equations pretty soon, but one thing we can already do that's always available to us is looking back at all the functions we've learned about so far and just kind of reasoning it out logically. We're trying to find a function whose derivative is just k times the original function. You know what? I think it's time for another useful problem-solving technique in math, trying to look at a simpler case first. So what would be simpler? What's the simplest possible value for k? Well, what if k was 1? That would mean that the derivative of z is equal to 1 times z, or just z. So we need a function that is its own derivative. Well, if you think about the derivatives we've learned so far, you might already remember a function that fits this description, e to the x, or, well, e to the t, since we're looking at population of zombies as a function of time. So the derivative of e to the t with respect to t is in fact e to the t. So a solution to the differential equation dz over dt equals z would be z equals e to the t. Great. But that's not the differential equation we were actually given, so let's go back to that. So we want to know what if the derivative of z is k times z. It sure would be nice if the answer was still an exponential function, but how could we modify e to the t to make it so that its derivative has an extra factor of k? Well, if we made it e to the kt, then when we take the derivative, we get e to the kt times the derivative of kt, thanks to the chain rule. The derivative of kt is k, so there's our extra factor of k. So that's a solution to the differential equation. Z equals e to the kt power. Let me reiterate that. This is a solution to the differential equation. It's not the only one. For example, z equals 2 to the kt would also work. When we take the derivative, we get 2e to the kt times k, again because of chain rule. So once again, the derivative is k times the original function. The same goes for pi times e to the kt, or negative 13 times e to the kt. In fact, for any constant c, the function z equals c times e to the kt is a solution to the differential equation dz over dt equals kz. So this is in fact the most general solution. Now often we don't actually want the general solution, but rather a particular solution that fits some given situation. And remember, we're trying to deal with a budding zombie apocalypse here, so let's get back to that as soon as we can. We know that at the beginning, at t equals 0 days, we had 10 zombies. That tells us that c has to equal 10, our initial count of zombies. Updating our model, now we've got z equals 10 times e to the kt power. Now we could plug in the other piece of information we know, which is that at t equals 1 day, we had 13 zombies. So that gives us 13 equals 10 times e to the k. If we solve for k using a little bit of algebra, we get k equals the natural log of 1.3, or about 0.26236. By the way, that number k is sometimes called the relative growth rate. So our final model for population growth is z equals 10 times e to the 0.26236t power. That should give us the approximate number of zombies in the student body at any time t measured in days. That's the particular solution to the differential equation that describes our situation. And what that means is that by day 18, we've already surpassed 1,000 zombies. And by day 19, it's over 1,400. That's terrifying. Now, before you panic, remember, every model has its limitations. Our exponential growth model works pretty well for a little while, but in reality, there's a maximum population of zombies, call it M, that the university can realistically support, what's called the carrying capacity. When there's a small number of zombies, it'll indeed look like we have exponential growth. But when there start being more zombies than uninfected people, that growth rate will start to taper off as zombies start having a hard time finding new people to bite. We can tweak our differential equation to account for this behavior by introducing a new factor of 1 minus z over m. When z is small, this factor will be close to 1, so it won't have much of an effect. But when z starts getting closer to m, the quantity 1 minus z over m will start to get smaller, closer to 0. And that means the shape of our zombie growth curve will look something more like what you see here. This is called a logistic model, and it's often used to measure anything that spreads, whether that be diseases, or rumors, or even social movements. In our case, we'll assume that the carrying capacity is 1,500. That's the approximate number of students at Oglethorpe, and that the relative growth rate is the same as it was in the last model. Problem is, solving this differential equation is a little bit harder, and actually it requires techniques outside the scope of this course. But we can still use this differential equation to get a good feel for what's going to happen numerically. Let's take our differential equation and multiply both sides by dt. So now we have dz, a tiny change in the number of zombies, is equal to our relative growth rate k, which is 0.26236 from the last version, times the number of zombies z, times that extra factor that makes it taper off as we get closer to carrying capacity, times the tiny change in time, dt. For right now, we're actually going to use a pretty big change in time, 1 whole day. So really, our d's should be deltas. And they'll be approximate, but they'll still give us a good idea of what's going on. Let's step through this bit by bit. At day 0, our number of zombies is 10. So if we let z equals 10 throughout this equation and delta t equal 1, then our delta z comes out to about 2.60611. That means that by day 1, we'll have that many more zombies. So if we add that on to our 10 zombies, we have about 12.60611 zombies at t equals 1 day. That non-whole number doesn't mean a zombie is missing an arm or something, it just means that we're dealing with an approximation here. But that's at least pretty close to the 13 that we originally counted. Okay, now what? Well, now the growth rate's going to be different because z is different. Z is changed from 10 to 12.60611. So if we plug that into our equation for z, we get that delta z is about 3.27954 new zombies. So now at t equals 2 days, that puts us at about 15.88565 zombies, give or take. If we keep going with this little by little, we can figure out the number of zombies and how it grows over time. Now we reach 1,000 zombies by day 24. But interestingly enough, now it takes another whole week before we pass 1,400 zombies, since things are starting to slow down by that point. That might just be what buys us enough time to figure out what to do about all these zombies. The method we used here is called Euler's method, named after Swiss mathematician Leonhard Euler. If you've seen the movie Hidden Figures, you've heard Euler's method mentioned by name. It's a method that's often used when it's difficult or even impossible to get a clean algebraic solution to a differential equation. So instead, your only choice is to calculate it little by little numerically. Euler's method essentially does a bunch of little linear approximations, linearizations, where you pretend your function grows at a constant rate for a little bit, then update the growth rate and keep going again and again. And if you use a smaller time step, you get a finer and finer approximation, which, when you think about it, is kind of the entire idea behind calculus in the first place. So, differential equations make use of many of the things we've talked about so far. Derivatives that describe rates of change, differentials that describe small changes and how they relate to each other, and even linear approximations that let us pretend a complicated function is just linear, just for a moment, so we can forecast what happens next. Differential equations find uses in all different branches of science, especially epidemiology. So whether you're preparing for a pandemic, or a zombie apocalypse, differential equations are an essential tool to have under your belt.